Thank you everyone for joining us tonight. I'm Matteo Madeddu. Thank you, Francesco, to let me have this session at the Talent Garden. It's the very first time for me. So we are gonna discuss about scaling image analysis in a real production scenario. So briefly, a bit more about me. I'm not really inside the data world in a sense. I'm more a platform engineer working mainly on AWS infrastructure. But the things I'm working in Prima Assicurazioni. The things I'm going to share with you tonight are not part of a use case we ran into Prima, but it was actually part of a real use case. I had the chance to work in a company I worked at previously. For the most curious, the company is Adidas. So briefly, the agenda of the speech. I will show you the scenario in a sense, even if you can already imagine what it is, but I will try to explain a bit better. Then we will go through the open technologies that are part of the entire solution we put in place to run this solution, and of course the AWS infrastructure we use to run everything. I will share with you some of the results we obtained that, in my honest opinion, were in a sense also impressive considering our starting case. Just a few lessons learned, and then if we have the chance, we'll answer your question, of course. So I'm gonna share with you a sentence that is pretty much my thoughts about, my experience around the last years in working in huge companies, small companies, startups, scale-ups, and the sentence is, let's make some data engineering. So the main goal of each company, I would say, in the world is collecting data, generating data, and then processing this data to get insights out of them, in a sense. So, and in our scenario, the company was a huge company, and so with a team of data engineers, that could be only one, maybe small companies. In our case, it was an entire department, and the assets, so the data we want to analyze, were pictures. You can imagine Adidas; it's a huge company, so lot of pictures actually. So the scenario pretty much worked like this. At least this was my impression, in a sense. So data engineers start working on a proof of concept, a POC, and suddenly it works. So this happens through iteration because it's part of data engineering itself. So trying to get some kind of insights, some kind of metadata out of images. Yes, it was a few years ago. I don't know if it is still the state of the art, but we ran into some TensorFlow models, neural models. I remember, as far as I remember, it was pretty much to get some shapes of products, this kind of stuff. So kind of analytics that cannot be done statically. We run, of course, also OpenCV. That is a pretty common tools to operate over images, so through colors and so on. And definitely it works on the laptop of data engineers, so with TensorFlow and OpenCV. That means for the company, let's put in production, because this is what happens. So when a pipeline, in a sense, start and you start getting some results out of this, the company want to push forward to get the results as soon as possible. And this is pretty much what happens when you run into this kind of scenario, and this is where platform engineers comes to help. So the scenario evolves in something that is, in my opinion, pretty much these are the steps that we run into when we try to get to provide helps to the data department. That is, make these things, this black box, working on each machines and architecture this is the very first priority for each platform engineer, in a sense. The second step is build a reproducible building process, so being able to reproduce the artifacts to run the models and so on. I will go into details about this later on during the speech. Designing a scalable infrastructure architecture to run this processing at scale. Of course, fix the scalable architecture, because there's always something that doesn't work as expected, or because people maybe has different opinions, different strong opinions around handling things through events and handling things in different ways. So this is pretty much what happened. Then finger crossed, hoping for the best, in a sense, and then let's put it in production. So this is pretty much the scenario evolved. Speaking about the open technologies, I wanted just to list not all of them, because to be completely honest, I don't remember all of them, and most probably it's also boring stating all of them. But definitely the first one I would mention is Python. We use it, Python, I will go through details around it, mainly to build a wrapper to collect these assets, these images, but also to wrap around the tools that were produced by the data department, to have a sort of common interface to create a direct dialogue to this model. Then, as I already mentioned, TensorFlow and OpenCV. Definitely Docker to build a containerized application to make this inference run correctly. And at the very end of this pipeline, there was an Hadoop solution, an Apache Hadoop solution, so distributed file system, as you might already know, and Apache Spark to process this metadata over this cluster. So just to summarize, the first technologies I mentioned, there were not all of them. There were many other languages, like I remember a few C++ and other languages to run some specific OpenCV task. In any case, these four technologies I mentioned here were used to get metadata out of our assets, in a sense. The latest two were pretty much used to process this metadata, so to get some more flexible format to better investigate, to better build dashboard and analytics over the metadata collected. Imagine this process done at scale. I will give you more insight around how much scale we are talking about. So this was the open architecture. I will share with you a really big overview of the AWS architecture, and please don't be scared, because the schema could like it seems complex, but it's actually really simple to understand. We will go through part, and the schema is pretty much this one. So everything will be fine. I like memes. I don't want to bother anyone anyway. Don't panic. We will see the architecture split into pretty much three main parts. And the first part is related to retrieving assets from an internal system, assets that we need to then process. Of course, this internal system has API rate limits, because the word is difficult to deal with. So this was pretty much our first limitation. Before going on with the very first part, I want just to share one thing, because maybe I don't know how much of you are confident with AWS services, don't want to deep dive into AWS services, because it is not a specific part of this topic, is more around the flow around the services. Just to mention one, that is AWS Elastic Container Services. The Elastic Container Services is a group of services, actually, inside AWS to run, to orchestrate container. No more than what you can do with a Kubernetes cluster. at that point in time, there were no capabilities from our side and no interest in investing into Kubernetes stuff. We ran into different Kubernetes cluster for many other topics. We used ECS by AWS, and this is kind of a sort of simplified version of Kubernetes. So ECS cluster inside the AWS are just metadata. You can create a cluster with no worker node. It's just a resource that doesn't mean anything. The most important and most probably the only things you have to remember for this talk is that you can run two different type of tasks over ECS cluster. The first one are Fargate tasks that run on managed infrastructure, so you don't have to provision any kind of worker node for this. The second task are just tasks that run on EC2 machines that are actually virtual machines inside the AWS world. So nothing different from having a pod running on a worker node of a Kubernetes cluster. Nothing different. So just a premise to summarize around this, because we are gonna run the two kind of tasks, so I want to point it out. This is the difference. So this is the very first part of the architecture. So is just cut and zoom over the very first part of the schema I shared with you before, and it's only related to the asset retrieval part. The asset retrieval part starts with the triggers of the whole process. One of the constraints, one of the desiderata of this infrastructure was to have something that has kind of near to zero cost if you don't have to process anything, excluding, of course, the cost of storage of the metadata you already collected in the past. So this is the reason there was some triggers. We run into different kind of triggers. The very first one is the CloudWatch event on a regular basis, nothing different than a cron job, so a scheduled rule that just trigger the whole infrastructure. The second one was a simple IoT button that is actually a simple device that you can program to trigger something on AWS. The third solution was to let developers through CLI, specifically in a programmatic way, launching the whole asset retrieval part. So the very first step was to run a Docker container containing Python code to get data from our internal system. Which kind of data? Not actually our assets, but a catalog of data, because our internal system has two kind of APIs. The first one is the one that provide you kind of list of assets. And this API has no rate limits. So, but we also had to put some logics behind this retrieval. So we we coded this super small application to get these assets, this catalog, in a sense, running some business logic. If you follow the number of the rows, it should be pretty clear. Get this catalog information and put them inside an SQS queue that is no more than a simple queue you can subscribe to. These queues are defined as a sort of retrieve jobs, so they contains the metadata required to then ask the same system through another API to get the assets. And this is the second part, so getting actually assets out of our internal system and storing them into S3. This was done pretty much for two reasons. The first one is to decoupling the two levels API, and the second one was to have a sort of copy of these assets in a scalable object storage. That was AWS at that point in time, but it could be actually anything. So having something that was reliable enough to support our request in the future for any further evolution of the system. So having this kind of copy of these assets that doesn't change in a sense because they are picture of products most of the times in a flexible object storage solution. So the Docker retriever is actually the same Docker image run with different parameters able to actually download these images. So at this point in time, we just get the images and store them in a flexible, in a flexible solution, in a sense, in a solution that by design can scale up to pretty much, without limits, because S3 is pretty known for this. So, but there's still a problem. And the problem is that, as I mentioned before, the solution that actually runs the inference still works only over the laptop of our data engineers, so our data department. And this is not to blame anyone. Our complex solution, you arrive by iteration, so they are complex also to pack, because it's not building a simple API, it's like wrapping a solution that requires a lot of libraries, a lot of locking, pinning of dependencies. They need to work in a certain way. The reasoning, the results you get are not, they are uncertain by default, by design. So yeah, this was the very first issue. Docker, we need you. The point was, we as a platform engineer, we ran into this kind of eternal loop, dreaming loop of having Docker images that is not about Docker specifically, but it's more about having immutable assets. So immutable artifacts you can run pretty much everywhere. So let's create an artifact, to run inference models and static analysis. 2,000 years later, this is something that is pretty complex to do, especially if you run into technologies that are complex to handle, as I said before, like TensorFlow models, OpenCV, with many dependencies, many different OS environments you have to simulate under the hood. But suddenly, we were able to actually pack this inference model. And this is the part where we run into the second part of our AWS infrastructure. Just to be crystal clear, the S3 bucket, the source assets, is the same bucket that we ended with in the slide before. In the very first part of the presentation. So I put it. I don't know if you can if you can see, but it's the same bucket. So the pipeline continues. The metadata, extraction part start from the bucket of assets. So the very first things to implement, in a sense, is notice, create a sort of event when a new asset arrive into our system, because we need to capture this new arrival. So we used a CloudWatch event, so nothing special. If you are not confident with AWS, it's just an event that is triggered when an object is created inside our object storage. And this event create a message that is spread through a dedicated SQS queue. So to analyze images, that image in specific. And the very core part of our solution is here, because the Docker container you see here is actually the Docker container that contains the solution provided by our data department. So TensorFlow models, OpenCV code to do static analysis, and so on. Everything is packed to run across a single image. This image is retrieved from S3, of course, thanks to the message that contains the reference to that picture. But the interesting point of this infrastructure is that we built a pretty complex solution about scaling the amount of jobs we were able to run. So at this point in time, the first things to notice is that the retrieval part is completely decoupled from the processing part. So you can retrieve assets a priori, without having, the needs of processing them in like 2 hours. At the same time, you can run processing completely in a separate part. And the scaling was done thanks to two scaling policies acting on the ECS cluster I mentioned before. This task due to the requirements of the models inside, need to run on EC2 managed by customer, by us, machines, worker nodes. So the very first point is how many machines I need to run in the more efficient way, the number of tasks I need to run, because I would like to be flexible enough to scale this process as much as I need. At the same time, I don't want to waste the resources because, I mean, I will pay for them. So, and we reached this result by putting in place a scaling policy that scale the number of EC2 worker machine. The more the number of jobs grows over our queue. The number of jobs inside the queue are somehow there's a metric that tell us how many messages is not an exact data, but how many the pretty much correct amount of messages that are inside the queue. These scaling policies so scale out our infrastructure by creating new nodes to give compute power to our cluster to perform the inference. At the same time, we also run into a step scaling policy that taking notes of the number of jobs as well, scaled up the number of inference model into the service that manage the number of Docker containers we want to run inside the cluster. So the scaling up and scaling out solution was able to take care of both the number of jobs in terms of how much of them I can run in parallel and how many machines I can I need to run them correctly. And what we came out with, it was a solution that was pretty straight to our use case, because starting from empirical evidence, we ran into a sort of table of machine family capabilities. So we were able to actually map inside our Terraform code, infrastructure as code, the capabilities of each different family instance type to run a specific amount of inference inference Docker container at the same time. So through the use of really one variable, actually a couple of variables, we were able to provide flexibility for our system to be modified in better, so to be enhanced in the future. In the case you have kind of a sort of new version of the inference model that was able to run in more than, let's say, five replicas over that specific machine. This was completely a disposal of our developers, our data engineers, data department in a sense. So considering both technical people and not technical people in a sense. At this point in time, if I didn't lose you, we have the assets, so our images, processed and metadata stored. The hand is near. I said three different parts, and I will go through the last part that is pretty simple to understand. Most probably you already imagine that. And the third part is pretty much like processing this metadata. So we have a results bucket that actually is the buckets where Docker containers stored all the metadata extracted by our assets. And this result buckets was a disposal of a Jenkins as a service deployed inside a Kubernetes cluster, actually, that was not part of this solution, was already in place in the company by luck, because otherwise it would be the most complex job of the world. And this Jenkins pipeline were able to do what exactly? To over specific events, looking at the results bucket, taking this metadata, launching a dedicated EMR cluster, AWS cluster. EMR stands for Elastic MapReduce, so is no more than a Puppet or something like this. I mean, a configuration management packaged by AWS to create managed Hadoop cluster. So it's actually Hadoop. It's just packaged around a service by AWS. So To do what? To have this metadata, of course, and of course with the help of Spark Jobs and so on, having this metadata ready to be used for data analysis and storage, so in Parquet or Abro or, whatever is the best format to support our use case, so to build also dashboard on top of it. There's also this super small part that is related to notification failure. We have a dedicated SQS queue to take care of errors or things that didn't go the right way by the runners, our inference model, just to keep track of images over which our models weren't able to get the metadata correctly. This SQS queues was attached to an SNS service to alert our most senior developers in such a way that it could investigate more over logs of specific run. So finally, metadata stored as Parquet Avro file are a disposal for further analysis, and this is the end of the AWS infrastructure to support this whole process. So you can be happy for this because I'm going to finish. So this is the schema I showed you in the very beginning. I don't know if by splitting it in 3 different parts, I make it more, I hope I make it more easy to understand the whole flow. It's pretty much simple because you start with trigger, you get these assets, you store them inside a dedicated bucket, and the inference model scales properly with a customization over tuning, how much money simply you want to spend to run this inference as much as the fastest way possible. At the same time, these results are stored inside the S3 dedicated bucket, and then a disposal for EMR and HDFS, analysis done, through Spark Jobs and many other tools. So, at the bottom part, you can see. Actually, there was also in the very first slide. I didn't say anything around this. Just a few words. This was part of my schema because this was the schema we put in place to let developers and every other people involved in this project being able to track the evolution of it. So going through Jira, Bitbucket, many other services. Just could be whatever it is, just ticketing system. Source control, Jenkins again, but it could be whatever it is, Quay, that is an image registry. We were able to run the evolution of both the infrastructure part that was coded in Terraform. I didn't mention Terraform, but it's still, and also, of course, the building of the artifacts itself. So the images, the TensorFlow model, and so on. Results. With our solution, we created an infrastructure able to scale this processing of images with no disruption for our internal system that was pretty, flaky in a sense. With cost near to zero, excluding the processing of metadata storage cost, and with the support of further tuning with the scaling policy, the reasoning we made around, the mapping between the capabilities of each different family instance type to run a different amount of replicas of the same inference model. We were able to run around, this was just one of our use cases, around 100,000 jobs, scaling from 1 hour of processing to get all the results stored inside S3, up to 24 hours. It depends on how much time you want, how much effort in terms of money and time you want to put into the processing, but still we were able to spawn through a huge window, and potentially even less, because actually the processing is completely a super parallelized process in a sense, so you can do parallelism potentially even all the 100,000 jobs at the same time in a sense. So lesson learned. Just one, and then I will finish. Hope to be in time. avoid creating black box code that potentially go to production. So this is pretty much, it could be like the common sentence. It's something, it's not like rocket science. It's pretty simple to understand. But the point is data engineering, as far as I see in huge companies like this, but also in other companies, smaller, is often around experiments and iterations. So you are not, you don't know exactly what are you doing until you reach results, in a sense. So no matter the pillar, my suggestion is that you should start with reproducibility in mind. I don't even know if it is an English word, but I guess you got the point. So my point is, good iterate over things. If something works, focus from the very beginning in making it work in the right way. So being able to pin dependencies, being able to reproduce the process, because otherwise you run into the difficult scenario of maybe working 9 months in fine-tune things, doing fine-tunings of things without having then clear extraction or clear, you lose some pieces under the way, during the journey. And yeah, it could be harder to then pack the solution to be production ready. So just start thinking about production ready solution when you have something working, even the smallest thing. Thank you for your attention. Sorry if I went too much faster. And yeah, these are the reference. These are the slides that are available on my site. And yeah, if you have any question, I'm here to answer. So thank you.
Whenever you're ready, Natale, now we are going to talk about Kafka and GitOps.
Yeah, in your honor, I'm bringing Kafka to the stage here, adding some bits of automation for Kafka. Yeah, so today we're going to talk about Apache Kafka and GitOps and how we get the best of the two worlds. So how we automate Kafka deployment, Kafka topics, Kafka action in Kubernetes. So the topics is having this in Kubernetes. So some buzzword about me. My name is Natale Vinto. I'm a developer advocate lead at Red Hat. Our role is to be, doing technical evangelism for Red Hat products that comprehends Kubernetes, Red Hat Linux, Ansible. I'm author for O'Reilly of those 2 books. I have some links at the end of the slide, so you can, if you want, you can download them also for free from Red Hat Developer Portal. I'm a continuous delivery ambassador this year. I'm really happy about it. And also Kubernetes Community Day program in the program committee. We had Aiven, I don't know if you heard about it. We have Kubernetes Community Day in June 16. It's an event about the Kubernetes community, Italian Kubernetes community. We have also the meetup, the Kubernetes meetup. And to finish my presentation, going to the actual topic, I'm a Red Hat certified engineer. So, data streaming is the future, right? GitOps is the future. Everything is the future. So how do we make sense of it? There's a wall of confusion, right? So the developers maybe care more about data streaming. No, I need Kafka. I need more streaming. I need those tools. And ops say, oh no, I need automation. I need to understand how to put that in place for you. This is what we call the wall of confusion. We want to stop this. We want to stop this, and we want to have collaboration between developers and ops. I see somebody of you are smiling. So now you tell me if you are a developer or ops. How many developers here? Just one, okay. 2, okay, not bad. So you are DevOps, a platform engineer? Oh, great, great. So I know you were smiling, so yeah. Did you manage to break this wall of confusion, or is it still there? Great, great. Yeah, so the idea of the topic of today is also showing how this can be possible in Kubernetes in particular, but in general, GitOps is an agnostic approach. And everyone here is the king. Developer are the king or queen. Ops are the king or queen. So everyone here is winning. The value really depends on the ability to deliver application faster. How do we do that? Automation, we do with compliance, security, and the ability to really automate everything. For cloud-native application, we've seen the talk before, or AI, machine learning, analytics, Internet of Things, and anything about innovation culture. And developer happiness, for you ops folks, developer happiness is really important because really can change the flow, also the speed on how your application are brought to production, and so ultimately in the hands of your customers. Today, I'd like to talk about this particular topic about Apache Kafka and Apache Kafka on Kubernetes. As you may already know, Kafka is a very popular open source software for implementing data streaming. So you have the ability to string messages. For instance, LinkedIn is made with Kafka. The inventor of Kafka did LinkedIn and then moved to another company. They did this but they released on the Apache Foundation, they give this project, which is Apache Kafka. So it's really also modern way to handle messaging, handle also communication between services. You don't do much REST today. You do kind of messaging through Kafka queue. This is good because it's store and forward, or you just asynchronous. So it's really, you are not waiting. You are not blocked on I/O. Too much AI. You're not blocking on that part. So that's very good. And there's an open source implementation on Kubernetes called Streamz. If you want to install Kafka on Streamz, you can have, the Kafka installation, manual installation, but also there's an operator that helps you having Kafka on Kubernetes. How many of you are aware of Kubernetes operators? Okay, most of you, yeah. Is a package manager for Kubernetes that brings some software and also some automation into Kubernetes. It's when you want to do stateful application or some more complex software, you likely do with operators in Kubernetes because it is integrated with Kubernetes lifecycle, reconciliation loop. So it's an advanced way to install application on Kubernetes. That's why when you really want Kafka on Kubernetes, you might look at Streamz because it's an operator that cares for you, the creation of the server, how many replicas, how many, for instance, you want to make a mirror maker. It's a Kubernetes API that creates a mirror maker for you. So everything is an API-driven object. The cool thing is declarative. In Kubernetes, everything is declarative. You declare, okay, I want this Kafka cluster with 3 replicas, and Kubernetes will make sure to implement it. But Kubernetes itself is not aware of how to make a Kafka cluster. That's why you need the operator. The logic is in the operator. Interested on Streamz? Streamz.io is the website. It's secure by default because it brings also out-of-the-box security best practices, support TLS and Scrum, and the protocol, automation in the certificate management. This can sometimes it's not trivial to handle certificate, issue and revoke certificate, right? Here you have a single point of control from the API, from this is in the Kubernetes terminology, is called custom resource definition. In that part, in that YAML file, you say, okay, this is the one, the certificates, those are the users, and everything, it's code base, right? You are Kafka as a code, basically. That's why it's configurable. You need some networking settings. You need some dedicated node of Kafka. You can program. It's really an enhancement of infrastructure as a code, if you will. And it's Kubernetes native because operators are first-class citizen, means are API native to Kubernetes. So you want to have the list of Kafka cluster in the cluster, you do kubectl get Kafka, really easy. Or you can manage Kafka using GitOps, which is the topic of today. Before showing it, let me show also an example of the how it looks like. When you install the operator, you want to install a Kafka cluster. Here's how to do that. Declarative. It's a YAML file or an API call, whatever. It's a YAML file. Okay, this is the name of the cluster. This is the version of, pretty old, this example. Replicas 3, I want 3 nodes. And what about the config? Is there TLS or not? The storage, ephemeral or some kind of storage. Zookeeper now removed, but if you want Zookeeper, you can add it this way and other things. So you can really configure with the code. And if you think about automation, if you have lots of clusters and you want to install Kafka in many clusters, you install the operator and then you bring this code. And some tool like GitOps can keep this code in sync. How many people here are aware of GitOps? Pretty good, all the ops, of course. Some expert dev, and this is good because GitOps is, for those of you not aware of it, GitOps is more a methodology than a technicality. And this methodology has 3 main pillars. The first one is Git is the single source of truth. So developers are really aware that Git is the single truth, right? Our application is on Git. Our microservice is on Git. Everything is on Git. But here, everything is on Git. And you treat everything as a code, the second pillar. So it's not only the code of your app, but also the manifest describing your app, but also policy as a code, security as a code, the networking as a code. Everything is code-based. Everything is declarative. And according to GitOps, every operation is made through a Git workflow. You need to change something in production. It's not a ServiceNow ticket or I don't know, a Jira ticket. It's a pull request, technically speaking. Then it's still a ServiceNow ticket, whatever you have in process. But technically speaking, is a pull request because everything is managed as a code and everything is auditable. That it's a developer-centric approach to continuous delivery and infrastructure operation. This is the main message. So, if you are not convinced yet of why GitOps, let me tell you in four message. It's using a standard workflow. Git is very familiar to any developers. Also, ops are familiar with Git because infrastructure as a code is something we have from some years today. And this enhanced security because you can review the change in production, in stage, in dev beforehand. You can, and not you, but the GitOps controller can detect configuration drift. So remember, Git is the single source of truth. If someone changed something on the cluster, then the tool need to revert because this need to go on Git. And can also take action manually or automatically. Visibility and auditing. You can capture history from the Git history. You don't see only the code of the commit on the application, but also the commit on the infrastructure. What this guy that stayed here for 3 days did and destroy my environment. Oh, this is what he did. You have all the review and through the Git history. And last but not least, if you are targeting multiple environment, geo-replication, high availability, multi-region, also in cloud, multi-cluster consistency. You have one cluster here, one in North America, one in China, one in Australia, whatever. You want to serve different clusters, different customers. Well, you need to keep this consistency. You need an automation that keep in sync the infra installation, and then an automation that keep in sync the app installation, right? This is why GitOps is very good. Let me show you the model for GitOps in general. So you have, when you use GitOps, you have at least 2 source repository. One is the repo of the app, of course. There are some pipelines, some CI that create an artifact and then likely a container image, then store this container image in an image registry. And here's the CD part, or if you will, enhanced CD, enhanced continuous delivery. The pull request or the Git action will sync the other repository, which is the manifest repository. So at least 2 repo. One is the repo of the app, or apps if you have microservices. And the other is 1 or more repo for the infrastructure or the manifest describing your application. The GitOps controller will push this into Kubernetes and pull any change from Kubernetes. It's a continuous loop. In this way, you keep consistency, and if you will, the system is also immutable. The GitOps controller does monitoring, detection of the drift, taking action, and deploying your app. This is in continuous loop. And one popular open source software for implementing GitOps is Argo CD. I don't know if you're already using it, trying it, but Argo CD is really popular. It's a CNCF project, and it's a declarative GitOps continuous delivery tool for Kubernetes. With Argo CD, you not only sync app, but you also sync cluster configuration. For instance, in your cluster, you need Streamz, and then you need other stuff. Then you need, I don't know, serverless. You install those operators, and then you install the app that consumes that operator. It automatically sync configuration from Git and detect this drift. We'll see more in the demo how it works. Granular control. There's a really nice dashboard I'll show you in a moment that lets you do sync and can manage also complex rollout. Very important, rollback, roll forward. If something really bad happened in Friday afternoon, 6, 7 a.m., and you are doing aperitivo and you don't care about your production, at that point, well, you can really easily roll back through the previous Git commit describing your infrastructure. And Argo CD will take that in consideration. Of course, if you have database migration, it's another talk, but we can discuss. If you are familiar with Helm and Customize, this tool supports Helm and Customize when you deploy application. And as a really nice view, we'll see in the demo in a moment, but this view show you all the Kubernetes objects in sync and also animate them when you need to do some change. So again, an Argo CD operates in two modes. One is polling. It polls the Git repo continuously and then take action. Or webhook. You send a Argo CD, you send a webhook to Argo CD, and Argo CD will perform the sync. Those are the two ways that you can use. So no time for more blah blah blah. Let's go into the code here with James Brown. What I wanted to show you is how to use Kafka and GitOps. And I'm using this repository from my colleague because I want to show you how he configured everything. So I cloned this repository locally, and it basically did this cool stuff. It created a bootstrap directory. In a bootstrap directory, he put basically the operator installation. So for instance, I need the Grafana operator. I need, and this is a subscription that subscribes to the operator. And then I need, this is, for instance, the operator for Streamz. The name in Red Hat as a product is MQ Streams, but it's the same. So you can have your repo for provisioning your cluster, and then you have a specific directory or part just for deploying your application. So this is an Argo app. What it's doing is deploying the bootstrap part and invoking Helm. This is another Argo app. What it's doing is, okay, go to this repository, go to the Kafka directory, and use Helm in the main branch, and use Helm to deploy all the objects over here. Target this Kubernetes cluster, and Argo CD also understands which cluster you need to connect. You can have a multiple cluster, right? Connected to one single Argo CD. Sync policy, if you want to Argo CD auto heal. So if you change something on cluster, it's gonna revert immediately. Or if you want some manual sync. If someone changed something on cluster, you keep it, and then somebody will reconciliate. There's the application for creating also topics in same structure, and also the user application. Let me show you. I already deployed it, but I wanted to show you one by one. So there was one app and I'm using, we're using Helm. So an Helm chart with values say, okay, I want Kafka 331 with 3 replica. And this Helm chart is really simple. Just go into the manifest as template. When you install the operator, you have those object available. So you can do kubectl get Kafka. And here, using Helm syntax, of course, what we are doing is, okay, install Kafka, and then this version with this replica, those listener, those configuration, you can, the partition, you can really customize everything, right? So this is still an infra setup, if you will. So somebody will set up that part for us. And then as a developer, maybe I can, create a Kafka topic as a code. So really I can create a YAML file and say, okay, I want this Kafka topic. I'm user one, topic one, for instance, and I want those topics. What are the user? Well, the user are also into the administration. You can create a Kafka user inside Kafka, or you can create a Kafka user inside for the topic. So for this topic, as this user, and those are the Kafka user that you want to add for each topic. The syntax look weird because we're looking at Helm, right? If you're not familiar with Helm, this is the syntax for looping or templating. But let me show you now the cluster itself. So this is my cluster. I'm showing you an OpenShift cluster. The OpenShift is a Red Hat Kubernetes enterprise version, but just as a visualization, it can be any Kubernetes cluster. So if you want to install Streamz, you can install Streamz by going to this website, operatorhub.io. You look for Streamz, and you look for instruction on how to install in any Kubernetes, whatever you are using, Minikube or any Kubernetes you have on cloud. Just install the OLM, install the operator, and then install the YAML file. What the operator brings is a set of custom resource definition. If you recall, the operator and then the API. Here's how you create a Kafka cluster, like we've seen in the snippet before. Kafka, my cluster, 340, 3 replica, no? I have the control on the code. So this is really, I think it's really ready for being automated, right? And this is the purpose of the demo. Now I wanted to show you this flow. I have deployed my Kafka cluster over here using Streamz and operator. I created a Kafka topic via YAML file. Actually, when you do here, you can also, this is just a UI thing of OpenShift, but in general, no? When you install an operator, you have all the API available, and if you want to create a Kafka topic, it's something like this. Create Kafka topic, it's just a YAML file, right, in the namespace you are working with. So creating a Kafka object once you install Streamz, it's really easy. Now, for the flow of the demo, I would like to show you how we can change permission on the repo, and then how Argo CD can sync everything. Argo CD here, what it's doing is syncing those 3 objects. So it's syncing the Kafka cluster. So this means that it's creating the Kafka resource definition. So if you want to change something, you don't change anymore from the operator or on the cluster. You change from here because the Argo CD will watch this file always. So there's also a discussion on who controls what. In this way, GitOps control everything. So the Kafka cluster setup is controlled by GitOps. You cannot change stuff which are not on Git, if you will, right? So the Kafka cluster is controlled by Argo CD, but also the Kafka topics, this topic, exclusive topic 2, shared topic 1. And if we go back, the Kafka user 1, 2, 3, 4. Now, let's do this. Let's go back here, and I was preparing the demo. So I'm using Kafka 331, and I'm using a producer and a consumer. Kafka was already there, sorry. Let me start from scratch because I was already creating it, maybe. Kafka GitOps. Get pods. Kafka producer. Okay, kubectl delete pod Kafka producer. Right on. Tmux attach. All right, so clear. Let me check if I am in the right Kafka GitOps namespace, and I hope you can look. So let's do the same. Create the producer. Okay. And then create the consumer. Let me check which namespace. Yeah. Consumer, right on. So here we're gonna produce something, hello, and we should likely see it here. Nothing really special, the producer consumer. This is user 1 writing on the shared topic 1. And this is the shared topic 1 with Kafka user 4. Now, all those credentials are on Git. It's not a good practice to put stuff on Git in terms of you have a secret and you should use another system to manage secret on Git. But for the purpose of this demo, just wanted to show you that, for instance, the user 1 is allowed to produce and user 4 is allowed to consume. What about we want to change stuff? And I was preparing here a script to show you a filed consumer. So now the user 3 is trying to consume from that from the producer. Let me show you here. We kill the pod. And so under the hood, what I'm doing is creating a Kubernetes pod representing a producer and a consumer. We should see an error here. We are not authorized to access the topic. So now what we have to do, according to GitOps, is change this permission on Git. Let's do that. Let's follow the flow. So we need to change this file, the user value file. Let's go in the Visual Studio Code so I can show you Kafka topic user management. Let me show you here. Here we go, and the file, if I recall correctly, for user value, right? So this is the file. This is the Elm file, right? This is just the Elm file. What really this is doing is creating a Kafka user API that is invoking the YAML, invoking the Elm file. So sorry for if it looks confusing, but this is just a way from Elm to inject file into the YAML of Kubernetes, right? The real value is over here. Once you install the operator, you have those first-class citizens, those API. You can do kubectl get Kafka user. And actually, I think we can try over here, get Kafka users. So I can show you. I can have the list of Kafka user like it was a pod. I can delete the user, kubectl delete. I can create in the same way, right? So that's the power of when you use an operator. But according to the flow, now let's see what we can do. We can change in line. I was putting line, no? In this part, we can change to exclusive topic to shared topic, because what was wrong over here is that we were trying to consume the shared topic, but user 3 is not allowed. So once we do this change, shared topic, right? And now user 3 can consume user 1. How do we do that? Well, GitOps. We need to open a pull request, and we need to perform this change. So let's do from here. We can create this adding to the staging area and saying adding permissions to user 3 to read shared topic 1. Okay, let's commit, and now let's create a branch from here, and then we can open a pull request. Add permissions. right? And we publish the branch. So now I don't have the GitHub pull request plugin from Visual Studio Code, but from here we should see that, okay, in this repository we have a new branch, which is add permission. Add permission should have this, this was done by now. We're changing this to that. Perfect. Let's open a pull request. Of course, it's not a good practice that I'm approving myself my pull request. It's really bad, but this is what we can do. So let's create a pull request. This is really the Git workflow. So not me, but for instance, another person, an admin, or can review that and say, okay, Natale wants to add to user 3 the permission to share topic 1. What happens is that I think this is okay just for the purpose of this demo, and I merge it. What happens? Argo CD is retrieving the change. So if we go on to the user and the topic and we refresh, we'll see that Argo CD is retrieving the change in the specific repository. This was also for the topic. So once we do that, we should be able, so now it was super fast, I cannot show you in real time, but the cool stuff is that Argo CD recognized the change and likely perform the update. Now, let's see if this is up and running. We have this merged into main, let's check. Exactly, this is merged into main, and now we should have our consumer able to consume. Let's see. Yeah. Let's wait a second. Okay, now it works. So really, really sample example, right? Really basic, but just to show you that a change in production is through a Git workflow, right? And everything is Git based, and Git is the single source of truth. This looks can be kind of not traditional way to do that, but it's also very convenient way to do that. In this way, you can really automate everything from the infrastructure to the application deployment. With that, I finished my demo. I just want to give you some final link here. So what we did today is showing that people, process, and technology create a cohesive platform. So platform engineer, DevOps, Ops, developers are all united into code. Everything is managed as a code. And talking about code, I can also share with you those links. You can download for free those books like Modernizing Enterprise Java, but also this book, if you're interested, is available on developer.com if you're interested on how to automate with GitOps your infrastructure, on how to automate everything. This is the book that you could use. I have actually also a hard copy with me, but in order to give you this hard copy, I would like you to play this game with me. This is another game. It's a GitOps-driven game. You have a two cars race, and you have to move your cars with a windmill. To move the car, you have to shake your phone. And it's a Quarkus Java application using InfiniSpan cache and Kafka to send the messages, and it's all GitOps-driven, right? In order to do that, please use your phone. I don't have mine here, but please confirm that you see something like enable shaking or permission from iOS complaining. They say, oh no, it's not available. Okay, click on enable shaking. Thank you. Now, let me go into the dashboard of the game, which this game is deployed always on Argo CD. This is the repository watched by this game. Those are the manifests watched by this game. And there is an automation. So Argo CD, there's Kafka, there's InfiniSpan, and there's the app. Now, I have the control here because I want to show you this dashboard. Let's check. We have 3 player in team 1 and 2 in team 2. The person that generates more energy will move the car. If you join the game and you don't move your phone, you're creating some penalty for the team. So the team is looking in. So if everything is fine and everything works, I don't know, it's live demo, who knows. 3, 2, 1. Please shake your phone, check your phone. Oh, team 2, wow, team 2 is super fast. Oh, congrats. But keep shaking your phone because at the end there's an overall ranking. Okay, team 2, congrats to team 2 that win the game. And the overall leaderboard say that Rosenman generated more. You are the winner, my friend. You are the winner of this fantastic book that I'll give you in a moment because it's in my bag over there. So that's a cool example on how we could automate with Argo CD and StreamZ. We could automate everything. And if I need to change something on the game, it's just one commit away. And in this case, there's a pipeline that automate my GitOps manifest. So here's the book.
Yeah, thank you so much.
Thank you, my pleasure. So this was my talk about today. I hope you enjoyed it. I left you those links. The books you can always download for free from here. And folks, if you want to try OpenShift like I showed today, there's this free cloud environment. As a developer, you can access for free and start deploying your application and testing your GitOps app, connecting to your external Kafka, like Aiven Kafka, whatever, you can connect everything. You can use this QR code to get this access. And yeah, that's all. Thank you very much for